Hello, hello. It's Jaden again, back from Total Developers, and today we will be going over the Bellman-Ford algorithm. This algorithm is used to traverse through a graph that contains negative weights or negative values, and it will return the shortest path for each node. Okay, so let's start. We can start by creating a public function called Bellman-Ford. This function should be of type vertice, which is just an ord and a copy. And we could write it like that. We could also try to make it prettier by doing this. Now we can do the same ord and copy keyword again, but add keyword with output equaling E, and then another one with negative keyword of type output equaling E again. Plus, we grab the standard library with the ops, and we add the sub keyword of type output equals E. Okay, great. So now we can start adding our parameters. In our parameters, we have the graph, which is of type graph. Which entails or is of type which has vertices and edges. We also have the start parameter, which is just a reference to the vertices. And our function should return the optional binary tree map, which has the vertices and an option tuple. Just entails the vertices. And we can set that equal. And then we can start our function now. Okay, great. So first things first is we use a like keyword, create a mutatable answer variable of type tree map with v and option keyword, which has the vertices, which is a tuple again with the vertices and edges. And then we just instantiate that with the new keyword. The rest it looks like this. Okay, great. So next is the insert into our tree map. We insert the reference to the start parameter as well as the none value. Then we start our loop from, or a for loop from 1 to the graph's length. Okay, and then we loop again through the edges in the graph. And we now take the variable distance of the u from the for loop above, and we get the optional vertice from that, the neighbors, then call sum again. And inside of here, we will have the tuple underscore d. This should return, or we call a function on some of a reference to d. As well as sum on none, which is calling the function none, returning on the function none, and none. Okay, great. So now we can start looping through our vertices and edges, or vertices and the distance in our edges array. From up here. And then we call the match keyword, and then we say answers.get. So basically, it's grabbing the neighbors of the current vertice that we're on, and we call some keyword, and then we call it some keyword again. And then we grab the distance, and then we ask if we have a match. So if match at distance u, we then want to either return a sum of distance u, and then calling the function on, take that parameter, calling the function on distance u, plus the reference to d is greater than or equal to distance. It looks like this. Or just none. And if it's just none, we will just call d greater than or equal to the distance. Great. Now, all this for the match statement. Now, for another sum statement, we would go something like this. For if it's a none keyword, we then do a match again on distance of u. Then we ask is sum of distance of u. We ask if distance of u is greater than or equal to reference to d. Call the function d, and then we close that. Basically, this is saying if distance of u plus d is less than 0, there's a negative loop going to start. Or else we keep going because it's just a longer path. So it looks like this. Reference of d greater than reference of d plus reference of d, and return none. Okay. Two, 4. Okay, and then if the shorter path, then we insert it into our graph, our answer graph. At that vertex, some look like this, and then it would be underscore u reference to u, and then we call a match keyword on the distance of u, and we check if it is a sum of the distance and then distance plus reference to d, or if it's not, we just return some or none. If it's not, we just return the distance or the reference to d. Okay. Just trying to make it prettier. Okay, great. Now we can start working looping side of the functions. And then we just say for u edges in the graph, let's run it again run the for loop again for all of the b and p in edges, basically all the neighbors in edges. Then we run the match. Dot get u, comma, dot get p. Some of none, some none, if e is greater than d plus reference to d again, and then that works out, return none. Or we have a sum of none, comma, sum of none, actually just sum of some, and then in that we have a tuple. Now we have a tuple called underscore dv. Then we say if d is less than dv, return none. Next we have another sum, but this time we have contains another sum inside of it, and we have the tuple underscore du, comma, sum and sum underscore dv if reference to du plus reference to d less than reference to dv, return none. And if nothing, oh, we still have another one to do. And then we still have to ask if the sum or if there is something that has the tuple, this one should go here, and this one goes down here. That has the tuple underscore the u. And we ask if some if that tuple has a none in it, and then we grab those values and then ask if the reference to du less than negative reference to d, return none. And then if all that, once we loop through and start populating or getting answers from our graph, we then, if nothing exists, so if all else, just return an empty array or empty object. And at the end of this, we return some for an optional answer. All right, from the Rust keyword. So let's check if this works. I'm expecting a few errors here, but let's see. Okay, where is this? Line 32. This should look like some this, and then we return du plus reference. We need to create that, a reference to that. Great. Now we have 46. We have an error on line 46. That is expected a insert reference to u, and then match distance u, distance. Expected this to be an enum. Should I insert vertex? Oh, I see. So insert should be like this. Should be this. This. Check it now. $70 says wrap this in some. Okay. And we have line 15. There's an error here. So it says option. C, B option B, E, goes new map. Okay. My return statement, we're expecting an option of B tree map. Where to see? and option vertices. Okay, that looks good too. Let's see here. I don't expected. It's saying that it's expecting an enum option, but it found just an empty answer. Okay, great. So we just needed a semicolon. At the end, we successfully built this, and you could go ahead and take a look at the code if you want. Go ahead and use it by all means. Use the tests if you need it. Yeah, and I'll catch you on the next video. Bye.